It is my pleasure to introduce Dr. Hans Stein for our speaker this afternoon. Dr. Stein is a professor of nutrition in the Division of Nutritional Sciences in the Department of Animal Sciences at the University of Illinois, where he has responsibilities in research, extension, and teaching. He currently directs 10 graduate students, 3 postdoctoral research fellows, 2 research managers, and 6 visiting scholars. His research focuses on feed ingredient evaluation, digestibility, and utilization of energy and nutrients by pigs and humans. Dr. Stein has won numerous awards, including the AFIA Award in Non-Ruminant Nutrition Research from the American Society of Animal Science in 2010 and the Bright Sciences Award from DSM in 2015. Dr. Stein is also an honorary professor at the National University of Columbia. He has authored or co-authored approximately 270 peer-reviewed publications, and he has given invited presentations on nutrition in 41 countries. Please help me in welcoming Dr. Hans Stein.
Thank you very much for the introduction, and thank you to the program committee for inviting me here. It is a great honor for me to be here today among this great outline of speakers, and what a nice conference this is. I want to congratulate not only Dr. Patience, but also everyone else who contributed to the conference. This is really special, so thank you so much for inviting me. So what I was asked to talk about today is a little bit different from what I usually talk about. It's kind of some vision, some thinking about how we can maybe get towards improved net energy systems. It's something I've spent quite a bit of time on thinking about for quite a few years, as you will see here. So I'll talk about quite a bit of things about what I have been thinking, what my visions is, what my conclusions are, and you'll not see quite as many research results as you maybe see in other presentations. So I'll start out by giving a little bit of background on net energy systems. What is we have today? Why do we have the systems that we have today? And then talk a little bit about what are some of the factors that go into developing a net energy systems if we are to decide to develop a new net energy systems. And then I'll talk about some visions I have for those for such a new energy systems, including I'll show you some photos of how we have set up a calorimeter unit that can be used for that purpose. So it will be kind of a walkthrough of my thinking about net energy. So that's what I'll try to do here over the next 40 minutes. If you look at the current net energy systems we have, there's really 3 systems in the world today that we can call systems. The first one is the one you all know, that's from France, the one that was designed by Dr. Jean Noblet. And I want to say here at this point that no matter what I say today, I am not criticizing Jean Noblet at all. He's a great friend of mine. I have known him for more than 30 years, and we exchange emails about every week, if not more often. And we don't agree on everything, but he's a great resource for me, and he asks me questions. If he has a question, I ask him questions. So nothing what I'm saying today is a criticism of his systems, but as you'll see as we go along, I think that maybe we can do some improvements to what we have today. So that's really all I want to do here today. The second system we have is chemical composition on nutrient digestibility-based system. That's a Dutch system that they use in the Netherlands today, and that is very similar to the Noblet system. And in fact, what the Dutch did, they borrowed all his diets, and then they reanalyzed them and did some other calculations, and that's how they came up with their system. So those 2 systems are very, very similar. Then the third system we have is a Danish system, and that's not really a net energy system. It's called PPE system. It's based completely on theoretical values for how many ATPs a pig can get out of each nutrient in a diet, and then with some adjustments here and there, and that's what they use in Denmark. But if you look at it, it's really the French system, the Jean Noblet system, that is dominating in the world in most countries, and that's also what we have here in the US. So one of the things that you have to keep in mind with these systems is that all the research that went into developing these systems, in particular the French and the Dutch, all that research took place more than 40 years ago. That means they analyzed the feed ingredients with the technologies they had at that time, they used the pigs they had at that time, and they used the ways to calculate digestibility that was common at that time. We have learned some things over 40 years, and so my thinking is that maybe if we implement some of the things we have learned, we can improve on those systems. So I really got interested in this quite some years back when I was involved in a pretty big experiment that was funded by the National Pork Board for different researchers, including Dr. Patience, who at that time was at the Prairie Swine Center, Dr. Ali in Missouri, and Dr. Pettigrew and myself from Illinois. And what the charge was for that project was to answer the question, are the European systems accurate under North American feeding conditions, and with the pigs we have in North America. And so what we did was we used the slaughter procedure. We fed pigs, we killed some pigs up front, we fed them for a while on different diets, and then we killed them again, ground them up, analyzed everything. And we have more than 700 pigs we ground up this way, growing pigs and finishing pigs. A lot of work at these 3 different research stations. And the overall result, this is from all the diets you see here. What we have in red is what we found in our system here in the US. This is what we got. If we had used the Noblet equation to estimate, we would have gotten this here in yellow. Dutch system, very similar to Noblet system, not surprising, in blue, and this is the Danish system. And you can see none of them were particularly accurate in estimating what we were getting here in the US. And as I said, this is more than 700 pigs. It's not just one little study. And we tried to challenge the systems, high fat, high protein, low protein, high fiber, low fiber, and so forth. But this is what we got. And that kind of made me think, well, maybe those European systems are not quite as accurate as we think they are. Later on, I served on the NRC committee, and we kind of looked into literature, and that's when the conclusion was made, well, we don't really have a choice. There is only the Noblet system. That's the only system we really have. So we either use that or we don't have a net energy system. So that's what we're going with. And again, I think that is a great contribution Jean Noblet has done, and he has put all his thinking into a system. He has traveled the world to try to educate us all about net energy, but maybe today we can do something better. So what I'll try to do here is just very briefly go over how energy is deposited in animals. And of course, it starts with the diets. All energy in diets come from either protein, carbohydrates, or fat. And the carbohydrates we can divide into the digestible carbohydrates or the fiber. But those are the 3 energy sources we have. If we look in the pig, we only have energy in the form of protein and fat because there's very little deposition of carbohydrates. But in addition to depositing protein and fat, the pig also needs energy for maintenance, and that's primarily in the form of ATP. So we have those 3, outputs that we need to do. So the pig needs to change the protein from the diet, the protein, carbohydrates and fat from the diet, into protein, ATP, and fat that is deposited. And there are some specific pathways there that can go. Protein in the body, amino acids in the body, can only come from amino acids in the diet, whereas fat in the body can come from either protein or carbohydrates or the fat we have in the diet, because all excess energy that we have in the diet will be deposited as fat. So that's just a brief overview. So when we go through the following slides, you'll see why we are focusing on protein and fat so much in our systems. Okay. Now, there's one other thing I want to touch on here, and that is the efficiency with which metabolizable energy is turned into net energy. And we already heard a little bit about that yesterday, and Dr. Patience had a slide in his presentation. This is a little bit more simple version of that same slide. You see the fat we have in the diet. If that is used directly for deposition of fat in the pig, that's very, very efficient. 90% efficiency is the estimate here. If we have starch in the diet, obviously it has to be digested, glucose is absorbed, and then that pig can deposit fat from that starch, and that's also very efficient, 82%. Protein, on the other hand, is less efficient. The for that simple reason that before we can deposit the carbons in the protein as energy, we need to do the deamination first. That takes energy, so the net contribution of energy from protein is less. And then the last thing is a fiber. And fibers have been estimated for anywhere between not contributing to the energy status of the pig and up to about 60% efficiency. And there's some reasons why there's this wide variation. It's how much do the microbes actually take from the pig when they have to transfer fiber into volatile fatty acids and so forth. But if you ever ask the question, why is the net energy system more accurate than the metabolizable energy system? The answer is right here. If all those numbers were the same, we would not need net energy, right? But because after we have accounted for digestibility of the energy, after we have accounted for metabolism of the energy, we still have differences in these efficiencies. And that's why the net energy system is more accurate, theoretically at least, than the metabolizable energy system. Okay, so what is a net energy system? And what do we need to know to construct a net energy system? The way I've been thinking about this, I think there are 4 things we need to know. And the first one is simply ingredient analysis. And I'll show a few examples here later why that is important. But we need to be able to accurately analyze our ingredients if we are to construct a net energy system. The next thing that's important is nutrient digestibility. We need to know how a pig digest nutrients and absorb them, because obviously the stuff that doesn't get digested does not contribute to the net energy of the animal. Those 2, I think, are pretty obvious. But another thing I think we also have to think of, and yesterday we had a great discussion about feed technology, and I think that's a part that we don't today have incorporated into our net energy systems, but I'll try to show you some numbers here that would indicate that maybe we need to somehow find a way to incorporate how feed technology can contribute to our understanding of what is the energy that is deposited in the pig. And then the last thing are animal factors. You've all seen data indicating sows have different energy digestibility or metabolism than growing pigs, and there may be other animal factors that we also have to think of. So those are the 4 areas I think are important for net energy systems. Starting with feed analysis, just a few examples here. Why is that important? Here I have data from the FEDNA table in Spain and NRC, 2 of the most commonly used feed ingredient tables in the world. Just showing DDDS. Here, this is a composition. We have moisture, crude protein, starch, sugars, fat, NDF, and ash. And the numbers are very similar for the 2 tables. Nothing really surprising here. But there's one problem here. The problem is this. If you add it all up, we only account for 90% of these ingredients. So unless you believe that the 10% we cannot analyze do not contribute any energy, you have to conclude that we cannot estimate energy from the feed ingredient composition here as long as we cannot analyze to 100%. So this tells you why feed ingredient analysis is very important. So what do we know about feed ingredient analysis when we have net energy systems? How do the current energy systems take care of this problem? Well, they take care of it in a relatively elegant way because they don't analyze everything. You see here's one equation from Noblet where we calculate net energy. They do a factor times the digestible crude protein, digestible fat, then the starch and the sugars, and then you'll see he doesn't have anything for fiber here, but what he has is a rest fraction, and this rest fraction is everything that is left over when he subtracts the sugar, starch, and the fat and the crude protein from 100. So instead of analyzing for the fiber or other fractions that are not included here, he just subtracts from 100, and then he has this coefficient there to multiply by. But that also means that whether we have soluble fiber, insoluble fiber, or oligosaccharides, or even disaccharides, they will all go into the same fraction here. And if you believe they can be utilized with different efficiencies, then we have a potential error here. Okay. Another way to do it, and this is another very popular equation from Noblet, is to bypass all that stuff and simply start out with digestible energy. Because if you start out with digestible energy, you have kind of said, okay, it doesn't matter if I cannot analyze all the oligosaccharides and stuff. If they contribute energy, I have it included here. And then he simply adjusts. If there's if there's more ether extract in the diet, he adjusts a little bit for that positively. Starch, same thing, a positive adjustment. Crude protein and ADF in this case, a negative adjustment. Critics of this equation, which is very popular, by the way, maybe the most used of his equations. Critics of this will say this is not a net energy system. This is just an adjusted DE system, which to some degree is true. It is an adjusted DE system, but if it works, I think that's not too much of a concern. But that's another way to get around the problem that we cannot analyze to 100%. Here's some fiber. This is one of my former students, Dr. Uriola's work, where we determined the disappearance of fiber in DDDS, and we had an overall disappearance of 49.5%, but when we divided that into soluble dietary fiber and insoluble dietary fiber, you can see there's a huge difference here. So if you want to be accurate in your estimates of fiber and how we estimate fiber contribution to energy, maybe we should at least be able to separate between the soluble and the insoluble dietary fiber. That's just one example of where we may be able to analyze more accurately and gain more efficiency. So that's just a little bit about why feed ingredient analysis is important. Here's another example how we can analyze that. And this is, to me, important because we can analyze soluble and insoluble dietary fiber on this equipment here. We bought that in our lab 5 or 6 years ago, and the longer we have it, the more happy I am with this because I'm convinced this is very accurate. And this is a not very complicated way of analyzing fiber. It is a little bit expensive. Dr. Payson said yesterday that he prefers the sugar analysis, and I don't necessarily disagree with that, but the problem is that the sugar analysis are less accurate than this one is. I'll show you an example of this. I have a student, Jimena, right now, and she's doing a study on metabolizable energy of sunflower meals. She has 64 fecal samples, and then after she had analyzed all of them for energy and asked if he could also analyze for dry matter, crude protein, fat, and ash. She did that, and we then subtracted the ash, fat, and crude protein from dry matter, and thereby we calculated all the unfermented carbohydrates. And that 58.2% in fecal samples in this case was unfermented carbohydrates. Now then, I asked her if she could also analyze these samples on the TDF analyzer and get the total dietary fiber analyzed, and she did that, and this is what she got, 56.3. That's a difference of 1.9%. That's pretty good in my estimation. So again, I think that total dietary fiber analyzer allows us to analyze for all the fibers in the diet. And I think that's the first time we really have been able to say we can analyze fiber in the diets. So I'm very happy with that. That's feed ingredients. What about digestibility? Going back to this equation again, you'll notice here the coefficient for crude protein is digestible crude protein, but that is apparent total tract digestible crude protein, right? That's what we use in our NE estimates today. Fat, same thing, apparent total tract digestible fat, and this is not even acid hydrolyzed fat. This is fat analyzed without acid hydrolysis, which we know is incorrect, in particular in fecal samples. Starch, 3.4, 18 times total starch, meaning there's an expectation here that starch is 100% digested. There's no digestibility value in front of that. I'll talk about that in a second here. And then there's the sugars, and then we have the rest fraction. But if you look at these three, crude protein, ether extract, and starch, what do we know today that was not known 40 years ago? Well, for protein, we know that we would use SID amino acids rather than total tract digestibility of crude protein. We don't have to discuss that much. I think that's pretty well accepted. So that's one area that probably could be done better than it's done currently. What about ether extract? Trey talked a little bit about that yesterday. Here's some data from an experiment where we fed different types of oil. All of these were corn oil, but in different forms. So we had liquid corn oil here, we had high oil corn, we had DDGS, corn germ, intact corn germ, and high protein DDG. Different amounts of fat in each ingredient. And then we fed them estimated true ileal digestibility and true total tract digestibility. And you'll notice here that if we feed corn oil, there's no difference between ileal digestibility and total tract digestibility. But when we feed all the other sources, we have a lower value for the total tract digestibility than for the ileal digestibility. Why is that? That's because when we have these intact ingredients, we put fiber into the hindgut, then the microbial growth increases, and the microbes, they incorporate fat in their skeleton, and that gets excreted, so we have more microbial fat here. That has really nothing to do with fat metabolism for the pig. It's just that the microbes, they turn some of those carbons from the fiber into fat, and they incorporate those into their skeleton. So clearly, the more accurate way here would be to do true ileal digestibility rather than total tract digestibility. So that's another example where maybe we can do better. What about starch? Remember, that was 100% assumed 100% digestibility in the equation. Here, 7 different cereal grains: corn, barley, oats, rice, rye, sorghum, and wheat. And you'll see none of them are at 100%. This is polished white rice here, and wheat, they are 98. And then we have some down to barley here at 85. So, yeah, the pig is very efficient in digesting starch, but it's not 100%. And I'll show you here in a little bit that starch digestibility does matter when it comes to energy. So, just these 3 things, crude protein, fat, and starch, I think we can do better than what is currently being assumed in our equations. Next thing was feed technology. How can we use feed technology? Well, one thing is particle size, and you'll see here we have an experiment where we had 4 different particle sizes from 865 microns down to 339. Linear increase in starch digestibility. Again, we said before, starch is not 100% digested, but we can get pretty high if we have a small particle size. What does that do to energy? Well, a linear increase in metabolizable energy as well. All of you know this. The finer particle size we have for cereal grains, the more energy we get out of it. So clearly, if we want to be accurate in estimating our energy, we'll have to somehow tie that into a particle size also. And I learned many, many years ago from Steve Polman. He told me it's a complete waste of time to publish values for metabolizable energy if you don't associate a particle size with that value. And that's a very true statement. So what about pelleting? This is a review paper we published last year. We looked at pelleting and meal compared with the same diets. Weaning pigs, nice increase when you pellet that. And this should be opposite. I'm sorry. This is the meal. This is the pelleted diet. The orange is pelleted. The blue is meal. So I screwed up on that. And the same thing with growing pigs. A significant increase when we pellet, right? So again, feed technology can help us increase energy. Extrusion, same thing from the same review paper here. We have the extruded in orange, the non-extruded in blue, and we see a nice increase both in apparent ileal digestibility of starch and also in the total tract digestibility of energy. And these are from all the experiments we could find in the literature on extrusion. So again, feed technology is important. And here's another one. What about additives? In this case, silanase. We have an experiment here where we had brown rice, that's primarily starch, so we did not see a response to silanase in orange here, but in full-fat rice bran and in defatted rice bran, a nice increase in digestibility of energy, or in ME in this case, when we added the enzyme to the diet. So again, we can use different forms of feed technology to maybe help us better estimate the energy we have in the diet. And somehow, if we can find a way to incorporate that into a system, maybe that can help us. What about animal factors? You have all seen data like this, where we have gestating sows in orange, growing gilts in blue, fed exactly the same diet, and you'll see corn soybean meal diet or full-fat rice bran diet, defatted rice bran diet, and we see a greater ME in the diets when we feed them to gestating sows than to growing pigs. That's pretty well known and also incorporated into some energy systems. But what about other things? Individual versus group housing of pigs. It's not hard to imagine these sows they lose less energy than these sows, right? They can huddle if it gets cold. They can bury themselves in the straw and so forth. So It has been estimated for sows that the maintenance energy requirement is reduced by up to 1,000 kcal in group house sows compared with sows installed. 1,000 kcal per day, that's 2/3 of a pound of feed every day, at least in the winter time. That's a lot, right? How do we feed our pigs, growing pigs? Always group housed, right? How are the net energy systems developed? Always individual pigs, right? So maybe we need to take that into account also. And here, at Libitum feeding, we feed pigs at Libitum in our systems, and at Libitum feeding actually gives us a little bit less energy than if we feed restricted. And at least in this experiment, we have tried to repeat this, and we get a little bit of variability among our experiments here. But it looks like, at least in this experiment, that at Libitum feeding is a little bit lower. We do feed our pigs at Libitum when we feed them. And so if you don't have that in a net energy system, you may also make a mistake. So based on this, I decided we need to try to design a better net energy system, and I don't have a particular good background in energy metabolism or in calorimetry. I pretty fast came up with the conclusion it needs to be based on indirect calorimetry. There really is no alternative to that. So I tried to educate myself a little bit about that, and because I feel that if we don't take advantage of what we have learned the last 40 years, then we will always end up with always use a net energy system that is not as good as it maybe could have been. And then you look around, who is going to make this update? And I started thinking about that. Instead, well, the Europeans, they're not going to do it. Noblet retired. In Denmark, they tore down the calorimetry units. In the Netherlands, they are focusing their calorimetry work on climate change gases. And so who is going to do it? It's either the Chinese or somebody else. And the Chinese will do it for sure, but maybe somebody else could do it, and then I decided maybe we should try to do that. So I went first on a world tour to try and educate myself a little bit about calorimetry. And the first place I went was University of Manitoba. Here's Dr. Miosotti showing me he has 3 little chambers, 1 pig per chamber that he's using up there. And he explained to me how he's doing it. In every place I took notes and tried to learn as much as I could. And so he was very nice and showed me everything he knew. I then went to China Agricultural University. They have a very, very nice facility there in the mountains outside Beijing. And they have six chambers here, very, very nice facility, and they are doing a lot of work up there. I went to France to see Jean Noblet one more time. His chambers are here in this building, here behind us here. And obviously he explained me a lot of things, and it's been very, very helpful. I went to the Netherlands, to Wageningen. They have this new building. This is all calorimetry, very, very flexible. They can have dairy cows or sheep or pigs or even broiler chickens there. But as I said, they use it primarily for greenhouse gas measurements and how that works. So that is a very, very nice facility also. I went to Brazil, in Sao Paulo, in Jaboticabal, and I visited a group there. They don't do calorimetry with pigs, but they do with chickens, and even they do some really crazy things. They try to measure energy metabolism in eggs before they hatch and see if we vaccinate the egg in ovo and stuff, how does that change oxygen consumption stuff. Very, very cool stuff, and I learned something there. And I also visited a couple of places here in the US. This is Michigan State. They have a nice facility, also primarily for environmental reasons that they have. And at UC Davis in California, they have this facility, and this hoop barn is 1 chamber. They use that with a group of beef cattle in 1 chamber, and they measure energy metabolism in the entire chamber, in the entire group. And that was kind of an eye-opener for me, because that told me, well, we can do calorimetry in group-housed animals, not just in individual animals. And based on what I showed you before with group-housed, I thought this should be important. So that was a nice visit. And then I went to Thailand also, and this is broiler chickens. This is CP Group there. They have a nice research facility south of Bangkok, and I'm lucky one of my former students, he's a vice president of research there, so he took me in and showed me all these things. And they have a lot of chambers here with broiler chickens, and again, you'll notice that these are group-housed animals. So I started thinking, maybe we can do group housed animals. Maybe we can do ad libitum feeding because that's what we do in the US. And I spent quite a bit of time trying to design my own calorimetry unit. And so I'll spend the rest of the presentation here talking a little bit about that calorimetry unit and what our visions for that is. So we will see here the Illinois swine calorimetry unit. It doesn't look very impressive from the outside. There's a reason for that. The first plans we had, we wanted to build a little building, but I quickly realized that in the University of Illinois system, if you want to build a building, you need to have Board of Trustees approval, you need to have the engineers, and when they told me I need to meet with the architectural committee, I thought, no, I don't need that. So this by definition is not a building, this is a unit, and because it's a unit, I don't need approval. So so this is sitting there on our swine farm, and that's why we have it. It was built by a company here in northeast Iowa, and we designed it together with them. So inside the building is 88 feet by 16 feet, and this is what it looks like. We have there's a corridor here all the way on the west wall here, and then we have the chambers and stuff over here. And I'll try and show you. The first room here is a feed room. It is an air-conditioned feed room, so we can keep the feed at a relatively good temperature there, so it doesn't go bad. Then we have 6 chambers: chamber 1, 2, 3, 4, 5, and 6. And these are about 2 by 1.8 square meters, so we can have different group sizes of pigs in there. Then we have 3 equipment rooms, 1, 2, 3, and you'll see they are next to the chambers. So we have 1 equipment room for next to each chamber. The reason we wanted it this way was that gives us the shortest lines with air. When we pull air from the chambers into our gas analyzers, that's the shortest line we can get. And I was advised by some engineers that you always lose air along those lines. So the shorter you can make them, the better it is. So that's why we built it this way. We also, I'll show you photos of these equipment rooms in a little bit. We have some other equipment in there also. We have a computer room here at the end. All the data from the gas analyzers go into a computer, and then we have wireless transmission to a computer room here where we can summarize everything up. And then we have a little mechanical room. We have a stationary power washer and a few other things there. So that's what we have in this unit. This is 1 chamber sitting here, and you see it's elevated a little bit. It's completely airtight, and we have tri-bar flooring, fully slatted. We have positive pressure, so the air comes in from in the ceiling here, and this is what you see here. And then under the chambers, we have screens, so we can collect feces, and you'll notice there's 2 fecal screens here. The reason for that is I was afraid that if we have a group of pigs in there and we pull out the screen to collect all the feces, then if some pigs they're defecating while we're doing that, then they will fall into the urine. We didn't want that, so therefore we have 2 screens so we can collect all of it. And then we have the urine screen here at the bottom, and we can collect all the urine also. So that's how we have it constructed. The equipment rooms, we have a couple of different things there. We have the fresh air supplies where we pump in the air into the units, and that's with an accuracy of plus minus 5%. And we have then the heating and air conditioning unit here, and that is a very accurate. Maybe this is overkill. I bought these from a company in North Carolina. But the reason I did it was everywhere I went, when I saw all these calorimetry units, I always asked those who worked there, I said, if you had to do it over again, what would you change? And all of them told me, we wish we had individual air control of each chamber so we can control the temperature and the humidity. So I thought that's probably important, so I wanted to have that. This is the most expensive thing we actually have in the unit here. These are very expensive, but they are very, very accurate, so we are happy with them now. And then we also have the gas analyzers here. You can buy gas analyzers from different companies. My gut feeling always is to buy German technology if I can get it. And there is German technology here available, but Siemens, they don't provide service in the US, and I was afraid of buying something I couldn't get service for, so we went with a company from Las Vegas called Sable Systems, and we have been extremely happy with them. They have excellent service, and the gas analyzers work very well. So that's what we have here. Okay. How do we do an experiment with what we have done until now? And I should say we started putting animals into this facility almost 3 years ago. The first year and a half, I kind of call it our commissioning period. We have to learn how to use it to prove that we could, if we fed the same diet in all 6 chambers, we could get the same net energy value in each chamber. So that's important. And we had some other things we tested. And we have kind of settled on a model now where we have 4 pigs in each chamber, so 24 pigs, start them around 30 kilograms and let them grow. They're there for 90 days, so there'll be 120 kilograms at the end. So we get net energy measured over the entire growing finishing period, which also changes, so I think it's important we get the whole period. 4 pigs per chamber, as I said, at Libitum feeding, and then we typically run our experiments as 6 by 6 Latin squares. So because we have the 6 chambers, we can do 6 diets. We have 6 periods, so we just rotate the diets among the chambers over these 90 days, 15-day periods. Here's one period. We have adaptation for 7 days. We collect feces and urine for another 5 days, and then the last 1.5 day here is what we call the fasting period. And during the fasting period, we take the feed out. There's no feed there, of course. And then we measure gas exchange during the last 12 hours of this fasting period. The idea is that the pigs, they will metabolize all the nutrients during the first 24 hours, and then we will collect gases here during the last 12 hours. Sorry. And this model here with 36-hour fasting is a model we have gotten approved by our IACUC committee, and so that's what they agreed to, and we are very happy with that. Here's one example. Just want to show one example from an experiment we conducted earlier this year. We compared the net energy in soybean meal to net energy that we have in the NRC values, and in this case you can see we have about an 8.5% increase in net energy, which is relatively consistent with some other data that have been put out over the last few years in terms of net energy in soybean meal, that it is probably underestimated in the current NRC book, and that's what we found here also. So we think we can handle the system. We think we can get reliable data. So where are we going from here? Well, we need to have a research plan, and the research plan is to get to a net energy system and not only have net energy in ingredients. We need to probably measure net energy in somewhere between 50 and 100 diets. We don't know that yet. We need to determine ileal digestibility of amino acids, starch, and fat in the exact same diet. So at the same time as we are running the diets in the calorimeter unit, we will also run them through pigs that are cannulated so we can get ileal digestibility values from those diets. And then we will do all the laboratory analysis we have heard of and we can do, and we've actually invested in quite a bit of equipment in our lab to be able to do that, so we can analyze for sugars, for fibers, for protein, and we just added an HPLC so we can also do reactive lysine, because that may also be important. We can do the physical characteristics, particle size, bulk density, and water holding capacity also. So we will try to analyze everything in those diets. So we have a lot of data, and then we will try to develop prediction equations based on everything, and hopefully not everything goes into the equations, but we want to know it if it has an impact. And then we will try to validate those equations, and then we will adjust as needed here. So that's the plan we have at this point. We haven't executed the plan yet, but that's the plan we have. To set up this system and the exact research plan, I'm planning to take a leave from University of Illinois next year, the first 8 months next year. I will go to Columbia, and the plan is that I will spend my time studying energy and think about these things and try to learn as much as I can of the things I don't know yet. And then I'll try to come up with a 5-year research plan that we hopefully can use to get to a new net energy system. And then another kind of important part here is funding plan. I'll try to get that also done, write some research proposals to try to get funded, and then I hope there'll be time to have a little bit of fun also. So that's the plan. So I'll come back here in August next year and hopefully have an idea of what we will do over the next five years. And if any of you are interested, we are open to taking money to support this work, so let me know. We have a small team. This is Diego Rodriguez. He's our research manager. This is expensive work, so I just want to show this. He's helped by Julio. They work full-time in the calorimetry unit. We have Dr. Funk, who is a retired engineer. He has helped us a lot, and you do need an engineer for this type of work, so he works part-time for us, very important, and he and Diego, they come up with a lot of crazy ideas, but they usually solve whatever problems there are. Then we have a laboratory, lots of laboratory analysis here. This position is actually not filled at this point, but this is my lab manager, Lady Torres, and she's taking care of all the lab analysis at this point. And then we generate a lot of data. Those gas analyzers, they generate a lot of data, the lab analysis and so forth. So we have one of my postdocs, Dr. Suarez. He's really good with data, and so she's doing all the summaries and all the calculations that we have here. So this is the team we have at this point, and I think we are well helped here. We need somebody else to take over some of Lady's duties here, but other than that, we're in place. So conclusions. Development of net energy system for group house pigs. That's what our vision is, and we will feed them at libitum. And we will try to base everything on the newest technology, newest knowledge we have about digestibility and feed technology and what else we know about nutrition. And we will have complete analysis of chemical and physical characteristics of these diets. That's our vision, and that's what we hope we can do in the future. So with that, I want to end and just thank my team. They are all helping here. This is our current team of postdocs, technicians, and graduate students. And again, as always, you can go to our website and you can learn more about what we're doing there. So with that, turn it back over to the chairman here.
All right, thank you, Dr. Stein. We'll now open the floor for some questions.
Dr. Stein, thank you for the great presentation. I just have a quick question on the soybean meal energy value.
Yeah.
Apparently, you showed and others showed the energy value in soybean meal, the net energy is actually higher than what we saw, right? But what does that really do to a commercial feed formulation? In terms of formulation. For swine nutritionists, what does that really? Because we're using soybean meal for the amino acid, right? Primarily,
Yeah, I think what it does it probably makes soybean meal a little bit more attractive in the formulations. But whether you should move your net energy estimates in the diets or not, I don't really know if I have a good answer on that, because you can say your current recommendations were based on a lower value for soybean meal, so maybe you should not move it up, or we should just move your targets up compared to what you're using now. But I don't know that. But it is possible, and I can't really wrap my head around that. The pig we have today is very different than the pig we had 40 years ago, right? Lot leaner, less fat. So, and because protein and fat is deposited with different efficiencies, what does that do to those values I showed you? Does a more lean pig mean that we are utilizing amino acids more efficiently now than before or not? And I cannot really, I don't have a good answer to it, but I know that there's some discussion, particularly in poultry, about that, and obviously the poultry, they are much leaner also. And it is possible that because we have better amino acid deposition in pigs today, that makes the protein ingredients more valuable than they were before. But I need to understand that better.
Okay, Hans, just to let everybody here know, the reason that we invited you to give that presentation today was that what you've created there is something very special for this country, and a capability that we either haven't had before or haven't taken advantage of before to do what you've described you're going to do. So I want to compliment you on your talk, but also on that initiative. That's a heck of a project you've taken on there, Hans, because for those of you that aren't familiar with indirect calorimetry, you really do need permanent full-time people running them. It's not like you can turn grad students over running an indirect calorimeter. So I just want to compliment you because it's a big deal. It's a big deal for us. And if I, in addition to that though, if I can just as you go to Columbia and when you're not having fun. I chuckled that you put that at the end instead of at the beginning. But anyhow, as you're working on developing your research program, I would like to encourage you, because I think the next step in energy will be to model energy as opposed to systematize energy. And as you put your program together and generate data, maybe keep in the back of your mind the data that might be used at some point in the future to create energy models. Okay, but and I think you're very capable of doing it. And I don't think it'll change very much what you're doing. It'll just make sure that data is available for the next generation. But anyhow, congratulations, Hans. That's a heck of a project.
Thank you. Thank you. Yeah.
Dr. Stein, well, as you were going to be thinking on ways to improve the net energy system, and you know very well Neil Jaworski, and I think his data on the kinetics of nutrient digestion, because we seem to put everything down to a total digestibility of the nutrient and then assume that it's all equal. And there has been, or his work suggests that may not be that the case. So it seemed to be useful to think what will be the next step on net energy, because we want to boil down something to a number that we are going to use to formulate, but may not always be additive. And I think fiber will do a big change of that additivity of the feed ingredients.
Yeah, I don't disagree with that, Pedro. As I said, I'm very excited about the way we can analyze fiber today that we have not been able to do earlier. And we also have in our lab, we set up the procedure to analyze for individual sugars. We pretty much copied the procedure from Dr. Bach Knudsen in Denmark and have that going. So we will be able to characterize the fibers better, at least, than has been done in the past. And I think that is an important part of the equation there.
We have time for maybe one more. Alrighty, seeing none, please help me in thanking Dr. Stein.
Thank you.